makes a difference, does it? Okay, it does? Okay, great. So as you know, the Simons Institute is a collaborative research institute in theoretical computer science. And it was funded in 2012 with a very generous grant from the Simons Foundation. And we run 2 programs a semester. And that has been since 2013. And you are one of the programs for this semester. And each program starts with a bootcamp, which is what we are doing today, and then has 3 more workshops during the semester, and brings even more people to the Institute. And this time we're running it in a hybrid form. So we have some people in the audience here, and there's a lot of people, I think, remotely as well. We have long-term visitors, a lot of fellows, and in particular this semester, we're very fortunate to have fellows, not only 8 associated with each program, but also NSF fellows and Simons Foundation fellows and quantum grant or quantum center type fellows. So we have 2 pods running at Simons these days. One is a quantum pod and one is a machine learning pod in parallel with the 2 programs that we're running. So as you know, the goals of the bootcamp is that you will get to know each other. So it's sort of an icebreaker, both scientifically and socially. And you get everyone on the same page as to sort of the broad spectrum of the field and what the program is about, and maybe have some archival state-of-the-art review. So I want to thank the organizers of the bootcamp and some logistics. I guess because of the pandemic, no food or drink, I think inside. We have the food and drink outside. In the auditorium, please, everybody wear a mask. I think the speakers have a choice also wearing face shields. I mean, we've got a lot of masks up front. So even though you don't see them, when you come in, you can ask for, either a surgical mask or there's a lot of types of masks out there. Lunch on your own. There are lockers here in the hallway for use at lunchtime. The Wi-Fi access, I think it's Cal Visitor or Eduroam, and everything is live streamed and archived on our YouTube channel. And a videographer is, who is it there? Is Omid there? I haven't seen him in a long time. There he's sitting over there. So if you have problems, you kind of wave him in and he will help you with connecting computers, microphones. And I think I want to thank also Kralani, who's the event coordinator. She's outside. She's outside, okay. And you can ask her if you have any questions. If you manage to recognize her through the mask, good luck to you. So welcome. I mean, I think this is really very exciting, and also the program is exciting. And I want to pass it to Guy.
Thanks very much, Shafi. Thanks also to the other folks who help run the Simons Institute, Peter and Prasad. Yeah, thanks to you. This whole the workshop and the whole semester is even happening. So we're very excited about that. And thanks, as Shafi said, also to the Simons staff. It's amazing how much they do and how little we then have to do as organizers. So thanks to all of you, and thanks also to the rest of the organizers for making the semester happen. So I'll say a few words about what the program is, maybe very briefly, and then about what is this boot camp and what you can hope to expect from it. So this program, its title is Computational Complexity of Statistical Inference. These are words that historically maybe haven't particularly appeared together in one phrase. And the reason is because these separate things have been studied separately. So statistics has been interested in how much statistical resource do I need? How much data or how much signal do I need in order to solve some problem? And this has been studied for close to a century, or for more than a century now. And a huge tradition of thought has risen there. On the flip side, computational complexity has largely been interested in how much computational resource, so especially time, but also memory and others, do I need to solve some problem. Typically, for instance, in combinatorial optimization, all the information that you need to solve the problem is there in front of you. And so you're not at all sort of data constrained. Of course, in the modern machine learning and high dimensional statistics problems, both of these issues are central, and they actually interplay in a really interesting way. And so this boot camp is aimed to give some context and give sort of an introduction to several of the schools of thought that try to study these questions. So in the first part today, Adam Klivans will tell us about a couple of modern, really interesting problems that sit at this interface where both computation and statistics are central. In the afternoon, Boaz Balak will tell us about a sort of view from CSPs, from constraint satisfaction problems. And that's a setting that's relatively well understood and for which many tools have been developed. And they can give us quite a bit of insight into the behavior that we might expect in these sorts of problems. As we move later in the week, Pulling Low will tell us about understanding statistical limits or information theoretic limits to problems. If we don't understand those, then we don't even have a baseline for what you can do without computational limits. So that'll be quite important for us. And then Prasad Raghavendra will tell us about restricted models of computation and how to think about developing optimal algorithms within certain classes for certain problems of interest. And finally, in the second half, or towards the end, Luca Trevisan will tell us about average case complexity. So when I say computational complexity hasn't been interested in statistics problems, there's sort of an exception because average case complexity, and which is intimately connected to many questions that people have been interested in cryptography, is very much about problems that are essentially, if you squint, are defined over data. And so he'll tell us some very interesting things in that context. And then finally, we'll have Cindy Rush and Andrea Montanari tell us about AMP and give us some insight into this class of algorithms that's optimal for a variety of problems, and how should we think about whether AMP is going to work or not work, and how do you analyze its performance. So with that, I'll hand it off to Adam Klivans.
Hey, thanks, Guy. I have a couple of questions for you before you go there. Can you hear me, first of all? No?
First off, Adam, can you hear us?
I can hear you, but
You can hear us?
Oh, wait, I sort of hear him super quiet.
You're very faint, I think is the only issue. Can you crank up your
For people
input?
online, you sound good. So
Yeah, maybe it's our problem.
Maybe it's our problem.
I'm great on Zoom.
Chris
Yeah,
says you're great on Zoom.
I'll wait for you guys to. I was going to ask. Well, I guess the people in the auditorium can't hear me, but maybe I'll type it. Let's see. Guy, can you guys hear me yet in the auditorium?
Good. So good.
Yeah.
Okay, so how are we going to handle questions from the in-person audience? They'll just speak up. I mean, that would be great.
I think we can try that.
Are they okay? That's fine. That's fine. That's fine with me. I mean, if they want to come to the podium, that's also fine.
There's a mic, right?
Yeah, I mean, if you can hear us, then presumably everybody on Zoom can hear who's ever speaking up as well.
Okay, I can sort of hear you. So, speak loudly if you have a question, if you don't mind.
Okay.
Okay. Well, anyway, thanks to the Simons Institute for hosting this program, and thanks to I am one of the organizers, but my co-organizers asked me to give this talk, and so thanks for inviting me, and thanks to Peter and Shafi for all the great programs that they've been organizing over the last couple of years. And I also want to thanks to my colleagues, Surbi Goel, Satan Chen, Fred Kohler, Raghu Mecca for feedback on this talk. And I'm really excited to be here. It's going to be a great program, and I'm thrilled to kick off the bootcamp. So as Guy mentioned, I'm going to talk about some problems from an algorithmic perspective that will touch upon sort of sample complexity and these computational statistical gaps. And I've titled these two talks "In Search of New Algorithms," and hopefully at the end of the two talks, you'll understand why. And the first part of the talk is all about neural networks. I'm Adam Klivans from the University of Texas at Austin. So the question that I've really been interested in for the last couple of years are, by the way, can you see my, oh wait, you don't have my slides. I see, okay, that's a problem. Just a sec. Okay, can you see that now?
Yes.
Okay, great. Yeah. So excellent. So the question that I've been really interested in for the last couple of years is, what are the most powerful algorithms for learning neural networks or for performing supervised learning on deep networks? And the current best algorithm that we have is backpropagation or gradient descent. I'm sure you're all familiar with it. But a question that I like to ask people is, do you think this will be the algorithm that will be running in 50 years in order to train neural networks? And I think it's a really important question. Supervised learning is sort of the engine that drives a lot of applications in machine learning. And also, I think it's a little bit this question of what algorithms are we actually using to train our neural networks to perform deep learning. I think it's a little bit under the radar. We've seen how important it is to have more data and to have more compute, but a really in-depth investigation of what are the best sort of algorithms that we have for training our networks. What are some interesting new algorithmic tools with provably efficient guarantees that we can develop? I don't think it's been studied as much, and I think it has the potential for great impact. We've seen that even small improvements on gradient descent or backpropagation can have really important applications. So this is sort of my big question. And the analogy that I like to make is one with sort of linear programming and the simplex method. It's been known for decades that the simplex method works really well in practice to solve linear programs, but only in the last, say, 10 or 15 years, I think, has the community sort of decided that we understand the complexity of the simplex method pretty well. And this is this important and seminal smoothed analysis paper by Dan Spielman and Shenghua Teng that I'm referring to. So it took a very long time before I think we had a satisfactory theoretical understanding of why the simplex method worked so well in practice. And along with the simplex method, if you think about solving linear programs or convex programs, we have a super interesting toolkit of methods for convex programming known as interior point methods. They've been very influential. They've had a lot of applications. And so it's really great that the simplex method has this sort of complementary toolbox of powerful, provably efficient algorithms. It's a real success story in theoretical computer science and optimization. So I like to think of gradient descent, or SGD, or backpropagation, as sort of a modern day simplex method. It works really well in practice. It's also very difficult to analyze. I don't think we still have a satisfactory understanding or explanation of why it works so well in practice. And even more to the point, I don't think that we have a complementary toolbox of algorithms, or at least a rich complementary toolbox of algorithms for gradient descent for training neural networks. And so I really want to focus on more of this question. I think understanding gradient descent and SGD is a super important research question, and I'm very interested in it. This talk is going to sort of ask the question, again, to ask you to think about, what are some provably efficient algorithms that we could develop in the coming years and decades to kind of complement gradient descent. Who knows, maybe we're leaving a lot on the table by not exploring this question as thoroughly as we should. So the goal of this bootcamp talk is going to be to sort of survey the state of the art for provably efficient algorithms for learning one hidden layer neural networks. And then I'm going to give you some examples of how you can actually provably go beyond gradient descent for some of these tasks. So that'll be the first part of the talk. Then in the second part of the talk, I'll talk about similar sort of agenda for graphical models, and hopefully I'll be able to tie both of these topics together. And so, as I mentioned earlier, if you're in the physical audience and you want to ask a question, please just speak loudly. And if you're in the, I don't know how we're doing questions. We're using the chat interface, the webinar, the Q&A. So hopefully someone will monitor that and at least let me know if you have questions. I'm happy to take lots of questions.
So I have a question. Just about your
Is that Shafi?
Yeah, just about your analogy.
Oh, hi, Shafi. Yeah.
About your analogy, the linear programming is in polynomial time, whereas learning one layer neural network, at least in the worst case, right? We know it's hard. There's a difference, but just in.
So actually, it depends on what you mean by hard. Did you say it's NP hard?
I thought that was Abraham's result many, many years ago.
Yeah, I'll get to that. So it's NP hard, but in a very restricted model. And kind of the point of this talk is going to be to show you how to circumvent a lot of those hardness results. Okay, so let me just define the learning model for you. The learner is going to receive IID examples, xi, yi, drawn from some distribution. And typically we'll work in the noiseless case, although we can talk about noise models a little bit. I'm happy to take questions on that, where we have some label y, and it's equal to c of x for some concept in some function class. And you can think of this function class for most of today, although at the end we'll go into deeper networks, as one layer nets. And then the goal, this is sort of the regression problem. The goal is going to be to output a hypothesis H such that the expected square loss of H when I see new examples that I haven't seen before is bounded by epsilon times the expected value of y squared. So one thing immediately to notice is that, and I'll emphasize this again as we go through the talk, I'm really interested in the complexity of outputting a hypothesis that has small test error, not necessarily small training error. So we want to do something more than small training error. We want to get small test error. And this is often referred to as simply pack learning. More recently, this has been referred to as sort of the student-teacher model of learning neural networks. I'll be using these terms interchangeably. And the reason why I'm calling this a regression problem is that we're looking at square loss here. Okay, and we could also look at classification problems. And the way I like to think about classification problems is, again, you're given xi, yi drawn from some distribution. And the y will now be a Boolean value, 0 and 1. But the conditional mean function is still real valued. So this c of x still could be a real valued network. But the conditional mean function, so the expected value of y given an input x, is going to be equal to c of x. And then our goal will be, again, to output a hypothesis with small test error. What does that mean in the classification setting? It just means that when I draw a new example xy, the probability that it disagrees with the Boolean label is now at most epsilon. And again, this is classification. Okay, so typically, until we get sort of to the end of this first hour, I'm going to be thinking about this function class as one layer neural networks. And the output y is going to be, so what is a one layer neural network? It's a linear combination of activations. So these lambda i's are the coefficients for these activations. This is sigma here, and it could be your favorite activation like tanh or sigmoid. For most of today, I will be considering the very popular ReLU activation, which just equals max of z and 0. And these wi's are going to be our hidden weight vectors. Okay, and so the main sort of distributional assumption I'll be taking throughout this hour, and this is part of the reason why the NP hardness results that Shafi mentioned are not going to apply, is that I'm going to assume that the distribution, the marginal distribution on X, is equal to just a spherical Gaussian. Okay, so it's sort of the simplest setup that you could imagine. You have a lot of information about what the marginal distribution on X looks like. It's a spherical Gaussian, and I'm just taking a linear combination of activations. And there's sort of two goals. Remember, in learning, we just want to come up with a hypothesis that has small square loss with respect to future examples. So I don't necessarily need to really fully identify these parameters, the wi's and the lambda i's. If you can do that, that's great. It's called parameter recovery. That's stronger than what we're interested in here, which is just going to be to achieve small test loss with some efficient algorithm. Okay, and I'm calling this the canonical setup because there are dozens of papers that appear on the archive every year that study this exact problem with the marginal distribution being Gaussian. And I used to sort of field a lot of objections about the fact that I'm taking this assumption that d of x is Gaussian. I've really relaxed. I've chilled out about it in large part, well, for a couple of reasons. One is that as you'll see as we go through the talk, it's a really great assumption to sort of clarify what's hard and where we can make new algorithmic progress. It also rules out a bunch of NP hardness results. But another reason for liking this Gaussian assumption is the power of generative models. So if you believe that generative models really do can form representations of images or faces, as we've seen recently, the way they work is that there's some Gaussian seed, and then you have a very complicated neural network or deep net, and it produces these sort of images that look very, very realistic. And you could imagine that you want to do downstream classification on these images that are output by a generative model. Well, if you compose the generative model with the neural network that's doing the object classification, then you really do start from a Gaussian distribution, and you end up with some classification problem on a downstream task. So I actually think that the Gaussian distribution, if you're interested in deep networks, is a very reasonable and interesting assumption. Okay, and this is sort of a technical slide. Don't get too worried about it, but since we're working in Gaussian space, we'll be looking at these functions that are bounded in some sense, that they're square integrable, and we have a natural associated inner product, which is just for two functions f and g, which is just the integral of f and g times the Gaussian distribution. And then if you work in this space, it's very well known in classical that the Hermite polynomials form a basis for this. Oh, okay.
Or more that they didn't refresh when you switch slide.
Oh, are they there now?
Oh, there.
Yeah.
All right, I think there was just some lag. Well, it's good. It was a technical slide. You didn't really need to pay attention to it. No, but yeah, these Hermite polynomials form a basis, and you can take the inner product of a function with the kth Hermite polynomial, and you get the kth Hermite coefficient. So these are the Fourier coefficients of the Hermite coefficients in this space. This is just so in the future, if I refer to Hermite coefficients, you know what I'm talking about. Okay, so let's talk about sample complexity for just a second. And I think it's important to point out that by any measure, this problem is information theoretically easy. So for example, if you consider the Rademacher complexity of these function classes or the VC dimension, or if you do something really naive and you just count the number of parameters that are involved in these function classes, then we know that the sample complexity for learning these one-layer neural networks or even deeper neural networks is polynomial in all of the relevant parameters. So the relevant parameters here are d, k, the number of hidden units, 1 over epsilon, that's the accuracy parameter. And what we really want is efficient runtime. And we may not be able to achieve polynomial time in all of these parameters, but at a minimum, we'd like to do something that's polynomial in the dimension, or at least sub-exponential in the dimension. And the reason for that is that, as I said, we're sort of interested in coming up with new algorithms. And if you allow me to run in time exponential in the dimension, then I can form sort of a net of neural networks. I can use brute force search to find a neural network that fits my training set very well, and I can just output that neural network. That's not the most exciting algorithm, and certainly it will be difficult to implement. So we want to try and avoid brute force search, and the way to sort of enforce that you're avoiding brute force search is going to be to, at the very least, require some sub-exponential in the dimension type performance. And I also think it's sort of instructive to ask, what happens if p equals np? Again, then learning is easy. Why is that? Well, there's some ground truth function from the function class that I would like to learn. I'm going to take a large but still polynomial size training set. As I mentioned, you can get away with polynomial size complexity in all of the relevant parameters here. And then I'll just guess a one-layer, say, ReLU network of smaller size that has small square loss on the training set. And because I've chosen a large enough but still polynomial size training set, and I've guessed a one-layer neural network that's smaller than the size of the training set, you can prove via standard generalization bounds that this network will have small square loss on future test examples. Okay, so here's sort of an easy observation. If we want to get an algorithm that has running time that's sub-exponential in the dimension, we could just remember that these one hidden layer neural networks really are juntas in the sense that they only depend on the subspace that's spanned by these weight vectors, these wi's. Okay, and there are only k of them. So if you tell me what the subspace is that's spanned by these k hidden weight vectors, if you were to actually give me that subspace, then it would be some k-dimensional subspace, again, spanned by these hidden weight vectors. And then I could do brute force search in this smaller dimensional space. And since k is a separate parameter from d, well, then at least for small k, I'm doing something non-trivial. And so kind of the first non-trivial question you might ask about learning these function classes is, can you find the relevant subspace that's spanned by the hidden weight vectors? Can you do this efficiently, or at least not pay exponential in dimension in order to find this subspace? Just, can we find the subspace?
Adam, why small k? Like from a modeling perspective? Like, is it just a choice to get yourself some tractable setting you can think about, or is there like some real world reason that small k makes sense?
Well, because we don't know how to do it. I mean, of course we would like polynomial in k, but at least this would get us 2 to the k, or something like 2 to the k, and that would be much better than 2 to the d. And hopefully that there's some interesting algorithm that's involved to kind of find the subspace. So I guess from a certainly in practice there are lots of dimensionality reduction techniques, and so I think it's still interesting to try and understand can we find the low dimensional manifold that our data is living on, say.
Well, thanks.
Is that Sam Hopkins?
That's me.
Okay. So if we assume that the lambda i's in this combination, for right now, let's assume that they're positive, then there is, let me start off by telling you kind of one simple thing that you can do. And this was actually in a very recent, I think 2020 paper of Diakonikoulos, Kane, Kontonis, and Zarifas. And what you can do is you can form this matrix. It looks like a PCA matrix I'm calling A, and it's the expectation of Y, the label, times XX transpose minus the identity. So it's sort of like a covariance matrix. And what they proved, and this was known for other activations, for all differentiable activations, as I'll mention in the future, although I think they were the first to actually write this down for the ReLU activation. You can prove that this matrix, if you look at its expectation, is actually equal to some constant times the sum of outer products, WI transpose, times lambda i's. Okay, so it gives you this nice outer product decomposition of the weight vectors. They just sort of pop out. It's not a difficult proof. And if you take sufficiently many samples to get an estimate of this expectation, then you can just, because the lambda i's are positive, we can apply the SVD algorithm to this matrix, and out pops the hidden weight vector. The hidden weight vectors don't necessarily pop out, but the subspace spanning the subspace, the relevant subspace sort of pops out here. I'll find a basis for my relevant subspace. And if you take enough examples, you have to be careful that you're getting a good enough approximation to this relevant subspace, because we have to just approximate this expectation. But you end up getting an algorithm with running time roughly k over epsilon to the k squared, and this wasn't known. So and there's also a polynomial in D here, but this wasn't known. So it's interesting. Even for k equals a constant number of hidden units, so for k equals a constant number of hidden units, this gives you a polynomial time algorithm, and that wasn't known.
Wait, why does it become exponential in k? This is because you're going to do brute force search in the k-dimensional subspace?
Yes.
Okay.
And I recently saw Dan Kane give a talk about this, where they gave a very powerful generalization of this result. And I really like the way he explained it. So I'm just sort of going to parrot his explanation. So another way to think about this is that, again, we have this matrix A, which is equal to the sum of outer products. And if we could take a vector V and just look at the quantity V transpose AV, it's easy to see that this is equal to the sum of lambda I V inner product WI squared. Okay, and this is going to be equal to 0 if and only if V inner product Wi is equal to 0 for all the i's. Okay, so this means that V's that satisfy this equality form a subspace of codimension K. And there's a very nice recent 2021 paper of Ilias and Dan that, so this is sort of what happens when, they view this as like a degree 2 polynomial. And they generalize this to higher degrees. So they look at higher order moments. Oh, okay. Sorry, Ilias is telling me this is from 2020, sorry. So they look at higher order moments. And the way that you do that is you can, it turns out if you look at the expectation of y, with x tensored to higher powers, you can compute polynomials of the form sum lambda I q of wi. So imagine q is a degree 2D polynomial. In particular, I can form a polynomial capital Q that takes in as input p and outputs the sum from I equals 1 to k of lambda I p squared of wi, just as we did before with the SVD. And here, this polynomial q of p is equal to 0 if and only if this polynomial of your hidden weight vector is equal to 0 for all i's. And what you can prove is that the dimension of this variety is at most d times k to the 1 over d. And in this paper, they have a very non-trivial construction of a net for this variety, but it is an efficient algorithm to construct a net for this space. And if you set all the parameters correctly, they actually end up getting an algorithm that runs in quasi-polynomial time. So they improve that k over epsilon to the k squared down to k over epsilon raised to the log squared k power. And again, there's a polynomial in D here. Okay, so sort of also to answer Sam's question, it's useful to think about this subspace problem because it can lead to more efficient algorithms. We didn't get a polynomial time algorithm here. We got they achieve a quasi polynomial time algorithm, but a very nice result. And this approach also applies to a lot of different models of latent variables, including mixture models.
Can I ask another question?
Yeah.
If you maybe five to 10 years ago, there were all these works on latent variable models via tensor decomposition where you didn't have to do high degree polynomials. You would just do degree 3, go from SVD.
Yeah, I'm going to talk about those in just a second.
Oh, okay.
Okay, so this is a very nice result. The main drawback is that we had to assume that these lambda i's were positive. And I guess sort of Sam, you're leading into this slide. Can we do something else? And the something else that we can do is something called, we can apply algorithms for tensor decomposition. Okay, so there's a different algorithm that we can apply, and this was a result I think that dates back to 2015 by Janzeman, Segdi, and Anand Kumar. And again, recall that we have some C of X, some one hidden layer neural network that we're trying to learn here. And actually, I want to assume that the activation now is continuous and differentiable, so it's not going to be able to handle, ReLU per se. The original works couldn't handle ReLUs, but you can get around that. And the main tool for analyzing or applying some of these tensor methods is Stein's lemma. And this lemma basically says that if you have any differentiable function C and you tensor it with X, then you get the expectation of the gradient of C with respect to X. So it's a nice identity. And as you keep tensoring up powers of X, then you get more and more, you take more and more gradients of the function that you're trying to learn. And so as we just saw, if you tensor one more time, you get the expectation roughly of Wi transpose. And if you, again, tensor one more time, then you'll get the expectation of something times Wi tensored to the third power. And the reason why these hidden weight vectors keep kind of popping out to higher powers is that you keep applying the chain rule as you're differentiating. And this S3 is something called the score function. And in Gaussian space, this is actually equal to the Hermite polynomial. But the main idea here is that instead of looking at expectation of y xx transpose, we can actually look at expectation of y, well, something like x tensor to third power. And then that actually gives us some expression that involves third powers of the weight vectors. And the bottom line is that by looking at expectation of y times higher order tensored powers of x, you actually get access to these linear combinations of higher order powered tensors of the weight vectors. And then you can apply these very powerful tensor decomposition algorithms. For example, we could apply Yenrich's algorithm to actually recover to within epsilon, so we could actually do parameter recovers. So once we have this linear combination of higher order powers of these weight vectors, you can apply a tensor decomposition algorithm and you can actually find very good approximations to these WIs. And if you apply, for example, Yenrich's algorithm, what you need is that the WIs are all linearly independent. And because we had an expectation, we had to sample, and we need to sample enough to make sure that our WIs actually look linearly independent, if they are indeed linearly independent. And when you do sampling, what you end up paying is the smallest singular value of all of these weight vectors stacked as a matrix. So for example, if my hidden weight vectors are very, very close in angular distance, then I'm going to pay a lot in sample complexity. It makes sense if the hidden weight vectors are very close in angular distance, then I need to take many samples in order to distinguish them. And these tensor decomposition algorithms actually will distinguish them. They'll give me the parameter recovery. Okay, so these algorithms are great, but the drawback, yeah, I guess, the main drawback of these algorithms, so they can handle lambda i's that are no longer necessarily positive, so we don't have to have positive linear combinations of neural networks, but we do pay in terms of this condition number of this matrix. So we pay if these weight vectors are very close in angular distance, or even worse, if this matrix is singular, then we're out of luck. So sort of you can't handle a number of hidden vectors k that's more than the dimension of your space. But this approach has still had many interesting applications. There's been a lot of related work. So for example, there's this very nice paper of Zhang, Song, Jane, Bartlett, and Dillon from a couple of years ago that used these tensor decomposition algorithms to come up with a solution for the one hidden layer neural network case for epsilon being a constant. So they get sort of a warm start. And then you run gradient descent to come up with a very accurate hypothesis. And they show that you get logarithmic convergence once you have sort of a warm start. There's a nice paper by Bakshi, Jerram, and Woodruff that combine tensor decomposition techniques with independent component analysis to come up with some incomparable results for learning one hidden layer neural networks. And there was a very, very recent paper of Awasthi Tang and Vijay Raghavan that can handle the case when these ReLU networks have non-zero bias, and also can handle sort of a smooth analysis setting of learning one hidden layer neural networks. But all of these works pay in terms of the condition number of that matrix where you stack the hidden weight vectors. Okay, so that's one drawback of all these results. Okay, so to summarize, for the techniques that I've described thus far, you either need to assume that the lambda i's are positive or that the WIs are well conditioned. And we'd really like to just solve one layer, come up with algorithms for one layer hidden neural networks. And maybe this problem is computationally hard, as Shafi sort of mentioned and alluded to at the beginning of this lecture. And I think conventional wisdom, what I feel is conventional wisdom on hardness results for learning these neural networks is as Shafi mentioned, that they're NP hard, that you can come up with these simple training sets such that finding very simple neural networks that have low error with respect to these training sets is very difficult. And why is that? Well, over the years, the field has figured out ways of encoding either hard combinatorial optimization problems or hard cryptographic problems. And one complaint about these results has been sort of, oh, well, the examples that you're looking at here are very discrete and Boolean, and they don't really occur in practice. They're very artificial. And so I think that as the years went on and people kept proving more and more sort of crypto hardness results or NP hardness results, people started to tire of these results a little bit because they felt that they were a little bit detached from some of the data sets that we were seeing in practice, and some of the constructions might have seemed a little bit contrived. Although I personally like all of these results very much, and I actually think that they're very important. So one result that I want to mention is a result that I had with my graduate students, Goel, Golakata, Jin, and Karmalkar. And what we proved is that there's actually something more fundamental going on than sort of encoding hard combinatorial optimization problems or hard cryptographic problems. There are more fundamental barriers for coming up with efficient algorithms for learning one-layer neural networks. And what we proved is a hardness result for gradient descent. That is to say, even if the marginal distribution on your points is Gaussian, and if you have any non-polynomial activation, so sigmoid or ReLU, doesn't matter, then unconditionally, we can prove that gradient descent cannot achieve a polynomial in the dimension or running time to learn one hidden layer neural networks. Okay, and this rules out a lot of popular approaches for coming up with for learning via overparameterization, such as the neural tangent kernel approach or the mean field approach. You can just prove that they can't learn the class of one hidden layer neural networks. So a lot of people ask me after I mention that, this, I don't understand what you're saying. This is very confusing. There are a lot of recent results showing that about the neural tangent kernel, showing that the NTK can actually solve one hidden layer neural networks if the marginal distribution is Gaussian. And that's not quite right. Actually, the main result of say, the neural tangent kernel is to show that if you overparameterize a neural network and you run stochastic gradient descent on it, then you'll get small training error. But if you want to prove that the neural network that you get after performing SGD on this training set actually has small test loss, then you need to take further assumptions. The results that I'm about to tell you about explain exactly why you need to take further assumptions. There's just no way of proving that you can get small test loss for this class, because we can prove unconditionally it's not possible. Okay, so more generally, we're going to prove two different types of lower bounds. One is a lower bound for something called correlational statistical queries, CSQ, and another is a lower bound for SQ, which is sort of general statistical queries. And these are probably two models that'll pop up in other talks during this bootcamp. So in the CSQ model, I need to force the learner to work in some model so that I can prove a lower bound against that model. And in this model, in the CSQ model, the learner is going to pick some function phi of x and then receive the following statistic. It will receive the expectation of phi of x times y, plus or minus some tolerance parameter tau. And in the SQ model, the learner can do something more powerful. The learner can pick a query function phi of xy and receive just the expectation of xy, phi of xy plus or minus tau. So the restriction in the CSQ model is really that y has to be multiplied by phi of x, your query function. So it's a very specific class of queries. But one nice thing is that it's easy to see that gradient descent falls into this class of CSQ queries. And so any lower bound that you prove for CSQ is going to apply to gradient descent. And so what we'll prove or what you can prove is that there's a CSQ lower bound for learning one hidden layer neural networks. It turns out in order to prove a lower bound in this CSQ model, it suffices to find a family of one layer neural networks or one layer ReLU networks that are almost pairwise orthogonal. That is to say, find a family of one layer neural networks such that for every two functions, f1 and f2, the expectation of f1 times f2 is at most epsilon. And if you had discrete distribution, so if our domain was the Boolean hypercube, then this construction is pretty easy. You can just compute parity functions, but we can't do that here because the marginal distribution is Gaussian. So that makes the situation a little bit more challenging. Okay, so let me just flash the construction here on this slide. So you can pick any, as I said, non-polynomial activation. And I'm going to fix some subset S of D of size K. And then I'll have this function G sub S that looks at the sum over all weight vectors in -1, 1 to the K. And it outputs some coefficient +1 or -1, which is equal to the parity of W, times phi of W inner product XS over root K. So the reason why I'm showing you this construction is just to show you that it's relatively simple. And it's easy to see that the size of this family is roughly D to the K, because S is a subset of D, of 1 through D of size at most K. And if I choose K to be log D, then you can see that the number of hidden units in every one of these functions is at most polynomial in D, because it's going to be 2 to the log D. So each element of my function family here is actually polynomial size, but I have I'll have a D to the log D. I'll have a super polynomial number of functions in this family. And these are the functions that will prove a pairwise orthogonal. So now you might be saying, oh, look, you're encoding parity here with these functions, but I'm actually not. This is just a coefficient. It's +1 or -1. So I'm taking many positive and negative combinations of this activation, but I'm not encoding the parity function. And to prove this, you just need this simple fact that if you apply a vector z component-wise to f, that the parity of z sort of pops out. You can pull it out of the function. And so if you want to prove that the expectation of f of s times f of t is equal to 0, because x is from a symmetric distribution, this is the same as choosing z at random and then looking at the expectation. And then I can pull out the parity of z. And then this is the two different parity functions, and their expectation for random z is going to be 0. So this zeroes out the entire, this shows that they're orthogonal. So I wrote down this proof just to show you that it's not a very difficult proof. Now, actually, the trickier part is to show that this family of functions is non-zero, but you can do it with an appropriate Hermite expansion, and this just gives you your CSQ lower bound. Independently from that same paper that I mentioned a couple of slides ago, Diakonikoulos, Kane, Kantonis, and Zarifas, they actually have a more sophisticated construction, and they get an exponential lower bound for one hidden layer neural networks. We got a quasi-polynomial bound. Okay, sorry about that. And there's also a hardness result, a very recent hardness result due to Danieli and Vardy that shows if crypto hardness for learning depth 3 neural networks with large biases, even if the marginal distribution is Gaussian. So they don't get crypto hardness for depth 2. That's another reason to study sort of one hidden layer neural networks. It seems to avoid a lot of these hardness results. So it turns out that this CSQ model is actually very different from the SQ model for real value functions. So we can obtain CSQ lower bounds for one hidden layer neural networks for gradient descent. If you want to obtain the full SQ lower bound, then you need to do, you need to look at the classification problem. So you need to let me take my one hidden layer neural network and run it through a softmax and do classification. If you let me do that, then you can prove the general SQ lower bounds. And we actually ran some experiments here. So we took this hard family of one hidden layer neural networks. And what you see when you run, what we did was we over-parameterized a neural network, we ran SGD on it. And the red line in these plots is the training loss, which as you can see goes to 0 very quickly. But the blue dashed line is the test loss. And as you can see, that continues to stay large. So even though you're running gradient descent on an over-parameterized network, and even though the training loss is very small, the test loss just stays very large. Okay, so to summarize, no CSQ algorithm can learn one hidden layer neural networks in polynomial time. That's what we proved. Now, about all of the algorithms that I mentioned at the very beginning of this talk, it turns out that they're all CSQ algorithms. Why is that? Well, they look at the expectation of y times something. As we said in the CSQ model, the queries that the learner gets to make have to be of the form y times some query function. So it was either y times xx transpose or y times x taken to some higher order power. These are all CSQ algorithms. And that's why they have to pay either, they require either sort of positivity of the coefficients or a bound on the condition number of the weight vectors. These assumptions, what this lower bound that I just mentioned shows that these assumptions are necessary for these class of algorithms. And we're in search of new algorithms. So the question is, can we go beyond the CSQ model?
Adam,
yeah.
Another quick question. So this is the hardness, like the fact that like constant order moment based algorithms are CSQ. Is the hardness sort of hiding in the tolerance here? Like, okay, here's the right question. Sorry. If I give you those moment tensors exactly, like forget the tolerance parameters in the queries, can you do learning? Is it identifiable? Like, are these things identifiable from, I don't know, 10th order moments?
Yeah, that's a good question.
Like, is it hiding in the tolerance is what I'm asking.
I think for general CSQ, that is true, that it's hiding in the tolerance, because if you don't put that constraint, then you can just query the answer bit by bit. But for moments, I think even polynomial accuracy is not.
I think those moment tensors are literally 0 for those controls.
Yeah, exactly.
Yeah.
I see. Okay. The point is that you can make a large family of one layer nets, and all the
Moments
like,
are 0.
moments are 0. So these. Okay.
I mean, you can estimate them pretty well.
I mean, the one caveat to that is that, you do lose this issue about, the condition. I mean, the reason why the condition number sort of comes in is that you need these sampling issues in order to get robust linear independence when you want to apply these tensor decomposition algorithms. So that issue will sort of go away to some extent, but you still will need like linear independence of the weight vectors.
And your construction does not have linearly dependent weight vectors, right? Like there should be linear dependencies in the weight vectors.
They are. Oh, yes, there are linear dependencies. Absolutely. Yeah.
Okay.
Good question. Okay, so we have these lower bounds for the CSQ setting, and we want to move beyond the CSQ setting. Can we move beyond the CSQ setting? So I want to go back to this problem of finding the subspace spanned by your hidden weight vectors. I mean, again, that's sort of the first task that we need to solve in order to have any hope of doing some non-trivial learning. And so in order to go beyond sort of the CSQ setting, instead of looking at the expectation of y times, say, xx transpose, we're going to look at, we're going to come up with algorithms that actually sort of choose, come up with some function phi of y. So we're not just going to look at expectation of y times something, we're going to look at the expectation of phi of y times something. Maybe that gives us some additional creativity that we can use to find the relevant subspace. And indeed it does. So one thing to notice is that, so I'm calling V here, capital V, the subspace, the relevant subspace spanned by these hidden weight vectors. And for any vector u that's in the orthogonal complement of V, if I look at U of mu transpose, so M is this matrix right here, you'll get that it's the expectation of phi times the projection of v of x into the relevant subspace times u inner product x squared minus 1. This is what this expansion turns into. And then right here, we'll use Gaussianity to split this expectation into a product of two expectations. That's because if the vectors are orthogonal, then as random variables, they're independent. So I'll get the expectation of phi of the projection of v of x onto v times the expectation of u inner product x squared minus 1. This term is 0. And so I get that the expectation is 0. So what does this mean? Well, this is at least a nice starting point. It tells us that vectors that are in the kernel of this matrix are actually in the irrelevant subspace. Okay, so that's a good starting point. And what we could hope is that if we look at sort of the singular value decomposition of M, that there will be at least one vector that's in the relevant subspace that we're trying to find. And that's kind of precisely what we're going to do. So what should be our choice of phi here? Obviously, we don't want to choose phi to be the identity function, but it turns out that we're going to choose phi of y to be the indicator function, that y is at least some value tau. And this type choice of phi was used in a prior work by Satan Chen and Regu Mecca for the case when you were learning polynomials of inner products of hidden weight vectors. And here we're looking at a one-layer ReLU network of weight vectors. So it's sort of a significant, it turns out to be a significantly different setting than the polynomial setting. But this is going to be the key choice of phi here. And this is how we're going to evade the CSQ lower bounds. Okay, and this leads me to sort of the main positive result. This is going to be the main example of an algorithm that can learn one hidden layer neural networks that gradient descent or any CSQ algorithm cannot. And this is from a recent paper, Learning Deep ReLU Networks is Fixed Parameter Tractable, again with Satan Chen and Raghu Mecca. And this time, we're going to look at deep networks, not just one hidden layer neural networks. So I'm going to be able to take my one hidden layer neural network and compose it with many different weight matrices and many different and several compositions of the activation function. And here I still want to find some function g whose square loss is less than or equal to epsilon. And what we're going for, unfortunately, we're not able to get polynomial time algorithm in all of the relevant parameters, but this algorithm will at least be a fixed polynomial in the ambient dimension d, an exponential in the parameters of the network. And this is the first positive result of any sort for learning ReLU networks of depth greater than 2 with respect to the Gaussian density. Even when all of those parameters that I'll mention of the network were held constant, no sub-exponential time algorithm was known. And it's the first example of a class of deep nets that can be efficiently learned by an algorithm and provably not by gradient descent. And just to tell you what the quantitative result actually is, the network parameters here that I'm talking about are going to be the depth, the Lipschitz constant, the size of the network, and potentially the spectral norm of all of those weight matrices. And the sample complexity of our algorithm is going to be roughly linear in the dimension times some exponential function of all of these parameters. And the running time will be quadratic, again, times some exponential function in all of these parameters. I don't think it's so important what the explicit function is. What's more important is that we're actually getting a fixed polynomial dependence for the sample complexity and the running time in the dimension. It turns out that this Lipschitz parameter is crucial. We actually you can prove that you actually have to depend on the Lipschitz parameter in some way. Okay, so again, instead of forming that matrix, so just looking at the time here, I think I'm going to explain this result, and then maybe I'll stop, and then we'll continue after the break. So we'll form this matrix, which is like a filtered covariance matrix. It's the expectation of the indicator function that the label y is greater than some tolerance tau times XX transpose minus the identity. So we call this filtered PCA because it's zeroing out a bunch of x's for which the label is not sufficiently large. And what we'd like to prove is that when you take the trace inner product of the projection into the relevant dimension V with this filtered PCA matrix M sub tau, and you look at its singular value decomposition, that the relevant vectors spanning this space actually appear. That's what we'd like to prove. So we'd like to prove a lower bound on the trace inner product of the projection into the relevant subspace times this matrix M tau. And if you do a little calculation, when you take the trace inner product with the projection into the relevant subspace pi of V, you get this expression, the expectation that the indicator is greater than tau, times the norm of X projected into the relevant subspace squared minus K. And what we'd like to do is pick this threshold appropriately. You can think of tau as being roughly root 2K, although we'll talk about it more later, but you want to pick tau appropriately so that if Y is sufficiently large, then the projection, the norm of the projection of X into the relevant subspace is sufficiently large. So as the output values of my ReLU network are getting larger and larger, I'm just hoping that the projection of X into the relevant subspace, the norm of that projection, is also getting larger and larger so that it becomes larger than K. And if it becomes sufficiently large, say it's 2K, then what I get is this expression that the trace inner product is going to be at least K, and if I look at this indicator, times the probability that my label is sufficiently large. So it turns out that you can choose tau to ensure that this trace inner product is at least K times the probability that my label is sufficiently large. And then that reduces our problem to really proving two things. One is that the probability that the label for a Gaussian random input of a ReLU network is actually sufficiently large with some high probability, namely that it's anti-concentrated. And also that when you look at the corresponding inputs to values that are sufficiently large, the projection of their norm into the relevant subspace is also larger than K. And why is this true? At a very, very high level for kind of two reasons. Well, three reasons. One is that ReLU networks are actually piecewise linear functions. This is very well known. And then because we have to look at a bound on the Lipschitzness of this ReLU network, it's easy to see that Lipschitz functions along a line in Gaussian space are anti-concentrated. So we're a piecewise linear function. We know that linear functions themselves are anti-concentrated in Gaussian space. And so if we apply the law of total variance, we know that there has to be sort of some piece within the deep ReLU network that is giving us enough anti-concentration for this analysis to go through. Okay, so what you can prove is that you'll actually obtain one relevant direction by looking at the singular vectors of this matrix. And what we were hoping for is that you could actually just read off all of the relevant directions from the decomposition of this matrix. That doesn't happen. And so we have to do something more complicated. We actually need to take that one relevant direction, subtract off, and repeat. So what we'd like to do is form this new matrix, which is the label Y minus the subtracted off portion that we just found times XX transpose minus identity. The problem is that we don't know F. So I don't know how to subtract off this projection of X into the directions that we've already found from the label that we have. And in order to do that, we actually need to brute force search over all possible functions F and prove some completeness and soundness conditions to make sure that this actually works. So so in order to subtract off the relevant direction, we need to prove that we can always find a new direction and that enumerating over all ReLU networks doesn't hurt us. It turns out that enumerating over all of these types of ReLU networks is even that is actually complicated, and we have to work with approximations to the weight vectors and the functions themselves. That leads to another level of complication. And so one of the main structural facts that we use to get around all of these technical issues is something from tropical geometry, and that's a fact about general piecewise continuous linear functions. They can and that is that they always have a max-min representation. So if you have a piecewise continuous function with m pieces, then I can come up with m subsets of capital M such that the ReLU network or any piecewise continuous linear function can be written as f of x is the max over all j and little m, the min over all of my subsets I sub j of these linear functions gi. And it turns out that this structural fact is what we need to be able to do sort of the brute force enumeration of these ReLU networks in small dimensional spaces and overcome a lot of the approximation issues that I mentioned earlier. Okay, so to recap, we can find one direction. We can use filtered PCA on the differences, on the residuals to find the rest of the directions. And this moves us beyond the CSQ barrier. Of course, what's still open because our algorithm is sort of exponential in the epsilon parameter is to come up with an algorithm that's polynomial time for even a constant number of hidden units and all of the parameters that doesn't take any of these assumptions about positivity or bounds on the condition number of the weight matrices. But I think the more interesting thing is that we found something that moves beyond the CSQ barrier and potentially suggests some interesting pre-processing steps before you would apply your typical optimization algorithms. So we're 12:40. I didn't completely finish my talk, but I have another hour. So I think we should stop here. I will, for the second hour, I'll just finish the last handful of slides because they lead into the second talk anyway. Does that sound okay, Guy? Okay, and I could stop here and take a couple questions if anyone has some.
If the number of WI is greater than its dimension, then probably estimate the subspace of this W as well. That's meaningful. That corresponds to the over complete tensor decomposition regime. So do we have any comments and suggestions?
I'm sorry. I'm having trouble hearing you. I'm sorry.
The question is about whether you can, what happens when you have more W's than dimensions? So
Yeah.
the over complete regime.
Yeah. So that corresponds to the over complete tensor decomposition regime.
Yeah. So so one thing you can say in that case, and this is enumerated, this is discussed. I was going to mention this in this Awasthi Tang Vijaya Raghavan paper, is that if the hidden weight vectors are smooth, so if they're chosen at random, then you can apply. You can still apply these. You can apply a higher order tensor decomposition algorithm, and things still work out. You pay sort of in the smoothness parameter, not in a fixed polynomial way, but you can say something.
Yeah, thank you.
Any other quick questions? Perfect. Well, thanks, Adam. Thanks, everyone. We have a short break and we'll be back.
When do you want to resume, Guy? I mean, we started a little bit late.
I think ideally, I guess it was 10. So let's still take 15 minutes, I think, and we'll resume at 10:55.
Okay.